Hello everyone, my name is Yifan. It's my great pleasure to be here to share our work, Efficient Training with Denoised Neural Weights. First, let's start with some background. Efficient training for deep neural networks can accelerate the model development process and reduce the computation cost. There are many works in the literature on efficient training, such as sparse training and low-bit training. Another important perspective is whether we can achieve efficient training with effective weight initializations. A good weight initialization can greatly reduce the training efforts. In the meanwhile, there are recent advances in hypernetwork design. It's an emerging topic in the generative AI area. The purpose of a hypernetwork is to generate model parameters. With the backgrounds, we know that effective weight initialization is important for stabilizing training, facilitating a faster learning rate, and speeding up convergence. Thus, it can enhance generalization ability. But identifying good weight initializations across different tasks is quite challenging. Tuning parameters for weight initialization can be time-consuming and also is prone to human error. This can cause suboptimal performance and increase training time. Therefore, inspired by the recent advances in hypernetwork design, we try to investigate if we can build a weight generator to provide better weight initialization across different tasks. Then let's move to the framework design. As we hope to show the weight generation ability across the models for different tasks, we take the generation of initialization weights for GANs for image-to-image translation task as an example. This is because it's easier to collect diverse datasets for the GAN model. But our method is general and is not restricted to predict GAN weights. And our framework is mainly composed of three key components: dataset construction, data format design, and weight generator construction. Next, I will talk about each component. For dataset construction, the critical issue is how to get a large-scale ground truth weight value dataset. And to achieve this, it actually follows three steps. The first is prompt collection, which provides the concept information. Then, given the prompt dataset, we can achieve image collection with diffusion models to obtain images, which is corresponding to each target concept. The images for each concept, they are further leveraged to train the GANs to obtain the ground truth GAN weights. And to get as many different prompts for styles as possible, we leverage a systematic approach with the help of large language models. We begin by defining three categories, which are the art concepts, characteristics concepts, and the face modification concepts. Within each category, we use a large language model to ask it to generate different concepts. And here, the large language model is ChatGPT 3.5. And to further enrich the prompt dataset, we permute and combine concepts across different categories. For example, we can get Superman in Vincent van Gogh style. Next, we further conduct an augmentation process. We query a large language model to provide concepts with similar meanings, but different representations. And here we use Vicuna for the augmentation purpose. After the prompt dataset collection, we use the diffusion model to edit real images. And after that, we can have the edit images for each concept in the prompt dataset. The edit images and original images form pairs of data, and they can leveraged for the GAN training process. And as for the GAN training, we use a generator with a hybrid of ResNet blocks and transformer blocks, which is used in previous work E2GAN. We apply low-rank adaptation, which in short is LoRa, to reduce the amount of weights to be predicted. And following the GAN training process, we can build a dataset of weights. And to further augment the weight value dataset, we save k different checkpoints through the training process after the FID performance converges. It's important to design the weight format for both training and inference of the weight generator, and there are multiple challenges for this. The first is that there are many different types of layers. Also, the size and dimension vary across different layers. Furthermore, the amount of weights to be predicted is huge. Even with LoRa, there are still more than 200,000 of weights to be predicted. And this requires a large weight generator with huge computation and memory burdens. To deal with this, we divide the weights into groups to reduce the complexity, and to make it possible for the weight generator to be fitted into the memory. We group the LoRa down and up layer for each layer I into one group. And if the layer is followed by a batch normalization layer, the batch normalization layer is also included into the group. After that, we flatten the weights into 1D vector and divide the weights into equal-sized blocks. Finally, we can get the data format, which is a tuple of the block index, the flattened 1D weight vector, and the test prompt of the current concept. Using our dataset of weight values, we train a generative model to predict weight initializations. We model the weight initialization space of GANs through a diffusion process. The generator is a U-Net weight information creator. And to incorporate the block index as a further conditioning mechanism, we compute the block index embedding and combine it with the time step embedding. The combined embedding is fed into the weight generator. After weight generator training, when there is a new concept, we can query the weight generator to predict the weight initializations. To make this weight initialization obtaining process faster, we use a direct reconstruction method. And after we plug the predicted weight initializations into the GAN model, we further fine-tune the GAN model to capture the details of the new concepts better. Finally, we come to the evaluations. We compare our method with 3 baselines. They are image-to-image translation methods, such as pix-to-pix. Pix-to-pix 0 distilled, that distills cool-mode GAN from pix-to-pix 0, and also with efficient GAN training methods, which is E2GAN. We evaluate our method both quantitatively and qualitatively. According to the results, the models obtained by our method can modify the original images to the target concept successfully. For instance, for the Jacob-Lawrence paintings prompt, our model generates more meaningful images compared to all the other baselines. And we also evaluate our methods quantitatively. From the results, we can see that with our weight generator, we can reach a better FID performance with a shorter training time. The FID performance is averaged across more than 40 different concepts in the test set. We also show the FID curves along with the training process by different methods. We can see that our method achieves a faster convergence, and it shows the effectiveness of our method. First, our method provides a better starting point for the training. It has a better FID score before the training begins, which is indicated by the performance at epoch 0. Second, training from the initialization can reach a better FID score, with much fewer training epochs. Besides, we conduct ablation studies on the block size and weight grouping rule. Due to the huge training cost of the weight generator on the entire training dataset, we conduct small-scale experiments for the ablation study. We overfit the weight generator on the weight corresponding to a particular concept. And any discrepancy between the overfitted results and the ground truth values can be attributed to the configurations directly. Setting a larger block size leads to a faster weight generation process. However, the FID performance is the best when the block size is set as 256. The generation time is slightly slower than a block size of 512. The results indicate that block size is important for the generator. And as for the weight grouping, we study 3 different rules. The first is to group the LoRa down, LoRa up, and the following BA layer, if applicable for each layer, to one group. Then we append the reshaped 1D weight vectors one by one. The second rule is to group the LoRa down, LoRa up, and also the BN layers into one group. But in this case, we concatenate the weights through the channel dimension and then reshape it to 1D vector. As for the third rule, is to view each layer as a single group and reshape it to 1D vector. From the results, we can see that both Rule 1 and Rule 2 can perform much better than Rule 3. And this indicates the importance of grouping the layers belonging to the same layer into one group. And here are more qualitative results. We show our results on different images and across different concepts. That's all. Thank you for your listening.